All right, let's do chapter 8, lesson 4. This is going to focus on one of the things that we have been working on the entire time as one of our long term goals, and that is getting to the law of conservation of mass. So let's get into it. All right, we have been looking at chemical and physical properties, and now we need to add in chemical and physical changes. The biggest difference is that a property is something that you can measure or observe, or we can also think of it as the ability to do something. And that not hasn't necessarily done it yet. It's the substance is just sitting there with the ability to do something that we can observe or measure. That is a property. A chemical or physical change is, well, that property actually comes to life and it actually does happen. So a property is the ability to do something. Change is, well, it actually happened. So as an example of physical property and physical change, a physical property of aluminum is that it has a melting point of 1,221 Fahrenheit, or about 660 degrees Celsius. Now, if you have a piece of aluminum, um, it may not necessarily be at that temperature, and so it is in a solid state. But it has the ability of melting once it gets to that point. If you actually witness it melting, then you know that it has gone through the physical change because of its physical property. For a chemical property and chemical change, a chemical property of iron is that it has the ability to oxidize, or what we call rust, when exposed to oxygen. If it actually does rust, then we say it's gone through a chemical change. So, you have four options. Physical property is something that can be measured, or is the ability to be measured. A physical change is something actually happened, but, and this is key, no new substances were created. We'll get into that in just a minute. A chemical property has the ability to change in some way, and in a chemical change, some sort of reaction actually happened, and this is big, a new substance was created. So, what actually does happen in a physical change? Well, it's form or appearance, what it looks like, but not what it is made out of. Its chemical composition is what changes. So, anytime something bends, tears, gets cut, melts, freezes, evaporates, dissolves, crushes, or anything else like that, you're not creating a new substance. You're changing what it looks like, but not what it is made out of. In a normal year, I actually use this lesson. And I ask my students, "Hey, can Mr. Bogdan borrow a pencil?" And I'll get a pencil from a student, and I'll say, "Okay, what is this pencil made out of? What's its composition?" And the students will say it's made out of wood and graphite, and then the little rubber eraser, and then the little metal piece that holds on the eraser. So that's what it's made out of. And then I'll snap the pencil, and the student's eyes get all wide. And I'm like, okay, what's it made out of? And it's made out of the same things: wood, graphite, rubber, metal. But what the pencil looks like is clearly different. So a physical change will change what the substance looks like, but not what it is made out of. Oh, and then I always have a new pencil ready to give the student, so they don't freak out. All right. Every molecule in the substance during a physical change remains the same. What happens in a chemical change? Well, long story short, the exact opposite. You get a brand new substance that wasn't there before, that is created out of the atoms in the original substance. Now, in order to do that, molecules in the original substance have to be moved around. Molecules can gain atoms, molecules can lose atoms, but molecules are going to change their formula, and that is what is going to create a new substance. So, physical change, no new substance is created, all the molecules stay the same. It just looks different. A chemical change, molecules get rearranged, atoms get moved around, and that is what is going to create a new and different substance out of the original substance. So, walk you through a couple of examples. The book is going to talk about types of chemical change. So, I wanted to take a few minutes to go through them. The first one that the book is going to cover is something called combustion. To give the simple explanation is that it is a rapid explosion or burning of of a fuel. Now, if I have a candle and I light it and it's just sitting there with a little flame, that's not combustion, that's burning. Combustion is a very rapid explosion or burning of a fuel. So, when a container of gasoline just explodes, that is a rapid explosion or burning of a fuel. What is actually happening in combustion is that a fuel molecule is being ripped apart and breaking down into new and different substances that are smaller, and so we call them simpler substances. So a combustion is a chemical change because a fuel molecule, the original substance, is breaking down into new and different simpler substances that weren't there before. The new and simpler substances are made out of the original substance, fuel. All right, so here is an example. All right, so when looking at diagrams like this, you want to find these arrows right here in the middle. That is your before and after line. So to the left of it, we have the original substances. They combine and they go through a chemical change. Now I get to my arrows. Now, after the chemical change, I have these new and different substances. So I've got methane and oxygen. Um, these are going to combine and then go through combustion. The methane molecule is going to break down very rapidly. And these four hydrogen atoms that are attached to the carbon atom are going to get plucked off, just plucked off. The oxygen atoms are also going to get ripped apart. Then, with all of these atoms hanging out, they're going to start reattaching into as new and different substances. So this one carbon atom goes here. These two oxygen atoms got ripped apart and they got stuck on either side, creating a new carbon dioxide molecule that didn't exist before. And it's made out of these atoms over here after they got ripped apart. Meanwhile, two other oxygen atoms are here and here, and the four hydrogen atoms get attached two to each, and I end up with water molecules, new and different substance that wasn't there before. So this carbon dioxide molecule and these two water molecules are new and different substances that were created during combustion out of the atoms in my original substances. So this diagram really shows a good example of a chemical change in that atoms get ripped apart and then rearranged into new and different substances. Um, and this is also a sneak preview to something we're going to be talking about, conservation of matter. So just as a preview to that, again, here's my arrows, the before and after. Um, one carbon atom before, one carbon atom after. One, two, three, four oxygen atoms before combustion. One, two, three, four oxygen atoms afterwards. And then one, two, three, four hydrogen atoms, a chemical change. One, two, three, four. So the amount of each element stayed the same. That's going to be important for later. Okay, the second kind of chemical change is called electrolysis. My simple explanation is that electricity is going to use its energy to break down a compound into simpler compounds or elements. So we're going to have a molecule, and then an electrical charge is going to rip apart that molecule. So electricity is going to break the chemical bonds in a compound, and that's going to give us new and different substances out of the original substance. So here we've got water. Okay, oxygen, two hydrogens, oxygen, two hydrogens. So I have two H2O molecules. Then here's my arrows. So there's my before and after. And then I use this symbol to symbolize that it was electricity that was doing this. So electricity is going to rip apart water molecules, and that's going to create new and different substances. I've got um, two hydrogen atoms that get plucked off of the oxygen atom and then stuck back together as just a hydrogen molecule. And then the same thing here. These two oxygen atoms, having had their hydrogens ripped off of them, they now find each other and they stick together. So electrolysis is going to take water and create new and different substances out of the water molecules, hydrogen molecules and oxygen molecules. The third kind that your book is going to talk about is oxidation. The simple explanation is that oxidation is when we see metal rust. And another example of oxidation is when apples start turning brown. So when you cut an apple and you leave it out, it's exposed to the air. Oxygen atoms are finding a substance inside the apple and attaching themselves to it. So oxidation is when oxygen starts adding itself to a molecule and changing what the molecule is going to be. So oxidation is when oxygen attaches itself to metal and causes rust, and oxidation is when oxygen attaches itself to something in an apple and turns it brown. So when you see oxidation, you need to think of oxygen. Oxygen atoms are adding themselves to molecules, making a new and different substance. So here we have two iron atoms, and along comes an oxygen molecule. And then the oxygen molecules are made of two oxygen atoms, and the oxygen atoms are more attracted to the iron atoms than they are each other. So they break apart, and one oxygen atom joins one iron atom, and we can see that here. And one oxygen atom joins the other iron atom, and that goes here. Here's my arrow for the before and after. And so two iron atoms and one oxygen molecule will oxidize and become two iron oxide molecules, or what we call rust. The fourth and last chemical change that the book was going to show you is something called tarnishing. The simple explanation is that it is the slow combination of metal atoms with another substance that is not oxygen, because that would be oxidation. And that's going to produce a dark coating on the metal. And that dark coating is a new substance that is similar to rust, but it's not rust because it didn't come from oxygen. Okay. So molecules on the outermost layer of the metal are having atoms or molecules that aren't oxygen added, which creates new and different substances. And we can see this in in true silverware. Real silverware used to be made out of the element silver. And silver, when it's exposed to the air, will start to develop, if as we go from left to right, this dark kind of uh, cruddy stuff on it, this on the outermost layer. It's not oxygen that's causing this, it's something else in the air that is causing it. And you have to, so as part of chores that a lot of children would have to do, is that they would have to clean the silverware. Nowadays, we use stainless steel instead of actual silver because it's cheaper and it doesn't do this. It's stainless, doesn't stain, steel. Here we have a bronze something, and after a while, being exposed to air, it will something besides oxygen will cause it to turn this darker color. So we call this tarnishing. All right. But no matter what, we have this big idea that we need to know in sixth grade called conservation of mass. Every atom goes somewhere in all changes. The word conservation has the word conserve in it, which means to keep or to preserve or to save. So we are going to keep or preserve or save all of the mass by accounting for every atom going somewhere. In both physical and chemical changes, no new matter is created, no matter is destroyed. Every piece of matter goes somewhere, even if it looks very, very different from what it used to. So here's a big, ridiculous example. I'll put myself in the middle where you can see it. Okay. Oh, it doesn't like me there. Never mind. We'll move it. All right. So what we have over here are uh, carbon dioxide molecules. And over here we have our Mickey Mouse looking water molecules. Oops. So going back to fifth grade, you learned about photosynthesis. Well, here we have the molecular explanation of photosynthesis. When you have carbon dioxide molecules and water molecules, the plant will take those molecules, start ripping apart all of the atoms and rearranging them into sugar. This molecule here is a glucose molecule. It is the sugar molecule that plants will make out of carbon dioxide and water. Now, what we're going to have is it really wants these carbons, which are the greens, and it really wants these hydrogens, which are the blues, and it needs a couple of oxygen atoms to make a sugar molecule. So all of the um, carbons, the six greens, become the six greens in the glucose molecule. All 12 of the hydrogen atoms get ripped off and stuck onto this glucose molecule. And to make glucose, you need six oxygens, so it used six of these oxygens. And so they are here. But the plant had a lot of leftover oxygen atoms, so it just stuck them together as oxygen molecules, and we have those here, and those just get released because the plant doesn't need them. But big idea: conservation of matter. Six carbons before, six carbons after. 12 hydrogens before, 12 hydrogens after. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 oxygen atoms total before. And we're going to have 18 total oxygen atoms after. You can go through and count. So yeah, the law of conservation of mass is during a physical or chemical change, every atom goes somewhere. No atom is ever created, no atom is ever destroyed. All right. The book is going to have a little section at the end on the relationship between matter and energy. Um, every chemical or physical change in matter also includes a change in energy. Energy is also conserved. That means that no energy is created, no energy is destroyed, but that's more for chapter 9. The book will talk a little bit about thermal energy. Temperature is a measurement of how hot something is, and it's an average. Thermal energy is a total amount of energy of motion of all particles in an object, but that gets more into chapter 9. So, temperature is a measurement, and it's an average of how much the particles are moving. Thermal energy is a total. All right. Thermal energy always moves from areas of high thermal energy to areas of low thermal energy. And your book's going to have an activity where you draw arrows. You have to draw the arrow or shade in an arrow which way you think the thermal energy is going to move. It's always, always, always going to go from the warmer object to the less hot object. The book is going to introduce you to two fancy terms: endothermic and exothermic. In an endothermic reaction, thermal energy is absorbed. For example, ice absorbs thermal energy from the atmosphere and then it melts. And in an exothermic reaction, thermal energy is released. So when a fuel combusts, you feel the heat being given off of that. If you're sitting around a campfire, the log burning is an exothermic reaction, and you can feel the heat that is being released. Whew, okay, so read pages 280 to 287, answer all of the questions. Take a look at the weekly guide, plan your week, and get to work.